Hello everyone and welcome to the channel Engineering with Kiran, dedicated to help engineers, draftsmen and students to understand the basics of engineering. I am Kiran Madhvi, Director of Tech Engine Solutions Private Limited, Mumbai. Over my 26 years careers in the structural engineering, I have the vast experience in designing the critical structures from flyover to complex extradosed and cable stayed bridges, marine jetties, and heavy industrial structures like NDCT and chimneys. Through this channel, I will share practical insights, lessons, and engineering philosophy that I have gathered over the last 3 decades. Please subscribe the channel and hit the notification bell. Let's build the future one step at a time. Welcome to the very first episode in this series, The World of Bridges. And today we are exploring bridge classifications. Before we get into classification, let's understand a bridge in general. A bridge is not just a structure. It connects people, their culture, cities, industries, and economics while overcoming the natural and man-made obstacles. Today we are covering the single most useful skill is in the bridge engineering, that is classifications. Not the boring textbook kind. Today you shall look up at the structure and instantly knows what it's called and why it's built that way. We are breaking bridges into four classifications. First is based on function, what job the bridge is doing. Second, based on the length, how big span we are talking about. Third, based on level, how it behaves in a flood. And fourth is based on superstructure, the actual structural system holding it up. That last one is the big one, 13 types. So stick around for that. Let us start the first classification based on function. This is the what this thing for is the question, and honestly most people can't tell or distinguish the flyover from an overpass. This will change now. First, the original definition. A bridge. A bridge in the strictest sense, a built across a channel, canal, creek or sea. It's crossing water. This one is the bridge over the Narmada at Hoshangabad, designed by Tech Tangent. Everything else on this list is the variation in the basic idea, just crossing something other than the water. A viaduct. A viaduct is what you get when the obstacle is not water, it's terrain. A valley, a depression, uneven ground, a long span, or instead of one long span, you use a series of shorter ones, marching across on repeated piers. This is the missing link viaduct between Mumbai and Pune, designed by Tech Tangent. A flyover. A flyover crosses another road, not terrain nor water. The whole point is letting vehicle keep moving instead of stopping at a signal. Notice the ramp on both ends. That's what makes it a flyover. Now an elevated road. An elevated road is a step up from the single flyover. Instead of crossing one junction, it runs parallel to the road below it for a long stretch, riding over signal after signal after signal. Think of entire elevated corridor cutting through a city. An overpass. An overpass is the simplest version of the one road crossing over the another. Just a clear separation so that two traffic streams never conflict. In the last slide we have seen the overpass. Flip the direction and you get an underpass. Movement goes below the reference road instead of above it. There are two types of underpasses. A PUP, a pedestrian underpass exclusively for the foot traffic, and a VUP, a vehicular underpass built to actually carry vehicle underneath. Now scale that up. An interchange is a full grade separated junction. Ramps, loops, directional flyovers built so traffic can move between two or more roads without an ever stopping. This is a cloverleaf interchange, one of the most recognizable interchange geometrics there is. ROB stands for Road Over Bridge, a road built over a railway track. If you have ever waited at a level crossing for a train to pass, an ROB is the engineering answer to never doing that again. RUB. The mirror image of the ROB is RUB. Road under the bridge. Same problem, opposite solution. The road dips under the railway line instead of going over it. FOB. The foot over bridge, exclusively for the pedestrians. Built over roads or railway lines. If you have used staircase and bridge combo to cross train tracks safely, that is also an FOB. And finally, a subway. It's a pedestrian underpass beneath a road, usually reached by stairs, ramps, or escalators. In this slide, we have seen the 11 structures. Every time we have to ask the one question to ourselves that what is the function of this bridge? Accordingly, we will remember the type of the bridge based on the function. Let us start with the second classification based on the length. This is the one simpler. It's really just three side stairs plus the one structure that is too small to even count as a real bridge. If the length of the bridge is less than 6 meters, then it is called culvert. There are two types of culvert, pipe culvert and box culvert. Both does the same job. Pipe culverts having the length less than 6 meters or more than 6 meters, it is called pipe culvert only and not a bridge. Cross that 6 meter line and you are officially in a bridge territory. From there, 3 tiers. A minor bridge goes up to the total length of the 60 meter. Beyond 60 meter total length, you will be launched in the major bridge category. And the third one is the long span bridge, specifically means a span length of 150 meter or more. Now we will see the third classification that is based on levels. This is about only one thing. What happens to the bridge when the water rises? A high level bridge sits above the highest flood level of the stream or the high tide level of the creek, plus vertical clearances and afflux. In plain terrain, no matter how bad the flood is, the level of the bridge is always above the highest flood level. A submersible bridge does the opposite by design. During flood, the roadway is deliberately allowed to go underwater. It sounds not good, but for low traffic rural crossing, it's often cheaper and smarter engineering choice than the high level bridge. And now the main event, the classification based on the superstructure. This is the classification civil engineers actually use on the job because it's tied directly to the span, that is how far the structure can stretch between the supports. We are going from 6 meter all the way to 2000 meter. Let's climb the ladder. Slab bridges are at the bottom of this span ladder. A solid slab is exactly what it sounds like. A flat concrete slab good enough for the 6 to 10 meter span. Beyond 10 meter span, solid slab gets too heavy for its own weight, so engineers hollow out voids inside it. Same shape, same look from outside, but a voided slab handles 10 to 18 meter span because it sheds a lot of dead weight. RCC girder bridges spanning 10 to 18 meters. Instead of slab of total width, individual RCC girders carrying load from the deck and transferring to the bearings. Simple, proven, and still one of the most commonly used bridges in Indian scenario. PSC girder bridges. PSC pre-stressed concrete girder handles 18 to 40 meter span, almost double what plain RCC can do. The trick is tensioning steel tendons inside the concrete before any load is applied, putting the whole section into compression. Concrete is great at resisting the compression and terrible at tension, so pre-stressing plays a very important role in improving the strength. The PSC-U girder is the next step up from the PSC-I girder. It has superior torsional rigidity, increased lateral stability during erection, and a reduced transverse span for the deck slab. A multiple PSU girder bridges covers 30 meter to 50 meter span range. And here is a new entry in the span range. UHPFRC-PSC girder bridges spanning 30 to 100 meter. UHPFRC is the ultra high performance fiber reinforced concrete, dramatically stronger and more durable than the standard concrete, which means girders can go longer and thinner than a conventional PSC section, with fewer piers and a lighter deck for the same crossing. This is the 60-meter span UHPFRC girder bridge at the Latur. Steel composite girder bridges. Swap concrete girder for steel ones and connect them to concrete deck slab with shear studs and two material act as one composite section. Steel handling tension, concrete handling compression. Same 30 to 50 meter span but different material story. This one is the SLR down ramp in Mumbai designed by Tech Tangent. PSC box girder bridges. Now we can go hollow. A box girder ranges from 35 to 70 meter span. Get its strength from closed box shaped cross section, which gives it excellent torsional stiffness for its weights. That's why it's default choice for the flyovers and long viaduct worldwide. You shall see four variations: single cell box girder, multi-cell box girder for wide decks, spine and wing for a slimmer profile, and strutted box which has the struts to support the wide overhangs. Steel truss bridges for span ranging from 50 to 100 meter. Triangle never lie. A lattice of steel members arranged in triangle carries load far more effectively than a solid girder using a fraction of material. Balanced cantilever bridges. For 70 to 180 meter span, you get balanced cantilever construction. Segments cast or erected symmetrically outward from each pier, balancing each other like seesaw until the span finally closes in the middle. This is the 185-meter central span bridge at the Bagchal, Himachal Pradesh, designed by Tech Tangent, a genuinely spectacular piece of engineering. Tech Tangent has been honored with the prestigious CEA National Award under the Innovation category in 2024 and IS30 National Award in 2025 in the Outstanding Structure category. Arch bridges, 70 to 250 meter span range, are the oldest trick in the book, literally 2000 years old. The shape pushes load down through the arch into compression, transferring it outward into the abutments. There are four types of arches here: deck arch, where the roadway sits on the top of the arch; semi-through arch, where the deck cuts through the pathway up; bowstring, where the horizontal tie replaces the need for the arch to push outward at all; and network arch is the improvement over the bowstring with diagonal crossing hangers and extra stiffnesses. Extradosed bridges typically spans 120 to 250 meters and represents a true hybrid between a pistless concrete box girder bridge and cable-stayed bridge. The main box girder is deep and stiff enough to carry a significant portion of the load, while the low-angle stay cables provides additional compression, improving structural efficiency. This is the Ram Manohar Lohiyapat Extradosed bridge in Bihar, designed by Tech Tangent. Cable-stayed bridges. Now the big leagues. Cable-stayed bridges ranges 250 to 700 meter. Cables run directly from deck to tower, putting tower into compression and cables in tension. That efficient direct load path is what lets these structures cover enormous distances with the relatively little material. This is the signature bridge in Delhi constructed by Gamma. Suspension bridges. Right at the top of the span ladder, suspension bridges ranges from 700 to 2000 meter span. This is a different system than the cable stayed. The deck hangs from the vertical angles, which connects to the two main cables wrapped between towers and anchored deep into the ground at each end. This is the Canal Bridge in Turkey, currently one of the longest suspension span, 2023 meter. When you need to cross something really big, this is what you reach for. That's all 13 superstructure types. Before we go, let's pull all together into one recap you can actually use. If you remember nothing else from this video, remember this table. It's your entire episode compressed into one cheat sheet. Span range on the left, bridge type on the right. Screenshot it, save it, use it, and that's a wrap on the bridge classification. Function tells you job, length tells you the scale, level tells you the flood behavior, and superstructure, the big one, tells you exactly how the structure carries its load from 6-meter slab all the way to 2000-meter suspension span. If this helped, hit subscribe. Next episode we are going deeper into the components of the bridge and their functions. See you there.